I thought I'd mention coils. Most hobbyists seem to avoid coils like the plague. There's a lot of hand wringing and frowning, stuttering. They're actually frightened of coils. I don't know why. They're one of the most simplest components you could get. They're just a piece of wire wrapped around a former. Here's one here. This one I've just made. Now, for this, I'll lead you through how I design coils. The main priority with the only main priority with an RF coil is you want it to cover the frequency that you're interested in covering. So let's choose a specific example. For this radio I'm building, which I stress is experimental, I don't even know if it's going to work properly, but we'll see. We actually want it to cover the AM broadcast band, which is 550 kilocycles or kilohertz to, well, it goes up to 1700 I think these days. So that's our coverage we want. That's all we need to worry about at this point. And we also know, well, once you've done this for years, and you made, well, you only got to make like a dozen coils for different frequencies till you figure out quite rapidly, you get a rough idea what you know, how many turns you need. Obviously you're not going to resonate the AM broadcast band with a 5-turn coil. The same token, you're not going to resonate into the ear band with a 200-turn coil. Now the more turns you have, the lower the resonant frequency will be. And there's formulas and there's nightmarish things, you know, ways of working this out mathematically, but who cares about that? That's just boring. I like just doing stuff without maths and without complication, because why complicate something that's actually dead simple? Now I happen to know, and you can cheat if you don't know this stuff yourself. You can cheat if you pull it back off, say, an old AM radio with a ferrite rod aerial or antenna, if you're American, bar in the back. You can see how many turns it's got on it. You know, it's got, I don't know, I've never counted one, but you know, there's got to be 100 turns on there. And because it's got a huge ferrite core down the middle of it, it increases what's called the inductance of the coil. So without that bar, we would need to have a few more turns on than what's there. And this is what these coils do. These here are generic coils. I wrap these because this old valve technology stuff, these old valve components now, they've been made for decades. They've been made since the middle of last century probably. So I wrap these things out of old radio gear. You know, anything I see that's got valves in it, I wrap the sockets, anything I can get hold of. And I don't care what these coils are originally intended to do. You just undo the wires, because the only bit you want is the coil former and the slug that goes down the middle. These particular ones, these are generic, all, even in America, all the old AM radio, the valve radios had these. So you just open the can, nice aluminium can, you open the can, there'll be a coil of wire in there. Rip the wire off and you can rewind them to your own specifications. The coil, the former is the important thing. In this case, these, most of them are the same. They've got the 6 little brass rivets in the base for wire terminations. You've got the circular cylinder, which is internally threaded to take either a ferrite or an iron dust core slug, or you can use brass or aluminium slug. A ferrite or iron core slug will lower the frequency as it enters the coil, whereas a brass or an aluminium slug will raise it up. Both aren't ideal actually. They take energy away from the coil and lower the Q. The best coils are actually air-cooled coils, but they were a pain. They were very, very difficult to adjust. You basically had to add or remove turns, which was an absolute nightmare, especially in mass manufacturing or mass producing of radio gear. So So what I'm saying to you here is that what we need to do is basically guess the amount of turns. We need a lot of turns. So with this one here, I figured out probably 150 turns to do it. I added on, I don't know, another 20 maybe, just in case. Yeah, it's easier to take turns off than it is to add turns on. So for argument's sake, if this resonated too low, for instance if it was going to cover from 450 to, I don't know, 1200 colour cycles, then it would obviously have too many turns on and I could take some off. Whereas if it went from say 700 to 2 megahertz, it would be resonating too high and would need more turns added, which is difficult to do because you've already wound the damn thing. So let's find out how we can resonate this coil and actually measure the coverage of this coil. Now this is the, if you remember, this is partly finished Synchrodyne Homodyne radio I'm building, designing at the moment. So I need a tuning capacitor just to make life easy. I could use that one, but this one here, I've got a swag of these things. So this is the tuning capacitor, identical to the one I'm going to use. Now what we're going to do, we have our coil, which is that, and we're going to connect that to our tuning capacitor to make this what's called a resonance circuit. So let's do that now. Let's connect this to our tuning capacitor. The iron's not particularly big enough to solder to the case of a tuning cap. It pulls a lot of heat away, but we will get there. Just perseverance and persistence. Okay, we now have a resonance circuit. Well, that's great, but how do we actually measure what that's going to do, or what frequency that's going to cover? Well, there's quite a few ways of doing it. Basically we just need to insert an RF signal into that and somehow detect the resonant point of the coil. So what we're going to do, there's several ways of doing that as well. First of all, what the system I'm going to use, I'm going to connect my oscilloscope to the coil. We're going to ground the oscilloscope ground to the one side of the coil. It actually doesn't really matter which side, but just to keep convention, we'll keep all the grounds to the case of the tuning capacitor. Put that there so you can see it. And we need to connect the input of the oscilloscope to the top of the tuning capacitor in the coil. But here we have to be a bit careful. If we connect it direct to the top of the coil, we're actually introducing stray capacitance in the cable. Depending on the input impedance of the scope, we're loading this circuit down. This isn't good. This will give us totally false readings. We have to somehow read the voltage or measure the voltage across that coil at resonance without affecting it with outside influences. So the easiest way to do that is we make a coupling coil. Have here just a piece of wire. What I'm going to do is just make a simple coupling coil. Sometimes with RF frequencies it's very difficult to measure something without affecting the thing that you're measuring. You've got to be very wary of this at all times. So here we've got what, about 4 turns, just an easy coil. And I'll move the camera in a minute, but here we have the, so now we've got, I'll show you what we're doing. So we've got out this coil in proximity to that coil there, so it's going to be coupled. Let's use that as a coupling. So we connect the scope. I'll move the camera in a minute so you can actually see all this working. And all we're going to do is insert that somewhere near the coil. That's all we really need to do. But we actually need a signal. We need an RF signal into that coil. So again, we have to be very careful that we don't load down the circuit. So what we're going to do is simply put in a resistor, a high value resistor, to prevent loading. So a good value is probably about 120 k ohms. This allows us to inject a signal into this tuned circuit, but not load it to any great degree. We still get similar results if we do load it more than we should, but it's best not to. So we're going to use a thing called a function generator. Now this pokes out, in fact my one is only a cheap thing, so I don't use it very often, but it covers from 0 Hertz up to about, I think it goes up to about 3 megahertz. So that's what we're going to do. We're going to connect the output, sine wave output of our SigGen, or our function generator, into the circuit. So we need to connect all our grounds together. So in effect what we're doing, we're injecting a RF signal at a known frequency into this resonant circuit, and we've got the scope connected, or the oscilloscope connected, to read the resultant output. So let's get this sorted. We need a, oh, I don't know, let's try a 100k, 120k ohm resistor, and we'll see if we can get this to work as I said it will. Probably not. It'll probably embarrass me. A lot of things don't work as you expect them to. So let's dab that onto the top of the coil. These old components absorb a lot of heat out of a modern soldering iron, I'll tell you that. Right, this is our lead from our signal source. That will go to there, to the tuning capacitor. Okay, have I told you a pack of lies, or is this actually going to work? Let's have a look. Just forgive the wobbling around for the moment until we get this right. Okay, there's our, see if we can get you out a bit here. That's better. Right, there's our oscilloscope over there, and there's our function generator. So let's turn the tuning capacitor to the lowest frequency, which will be full capacitance, the vane's fully closed. And as I vary the frequency of the, we'll see what the oscilloscope's telling us. Hope you can see that. Oh, no, what's going on there? There we go. You can see the resonance peak there. So if we get that to the peak at its greatest level, we can then look at the frequency on the function generator. You can see we're about 620 829 kilohertz, which is slightly too high. We really want it to be a bit lower than that. So now if we change the capacitor to minimum capacitance, once again we'll look at the scope and I'll vary the wrong knob. Try doing the right knob. We'll lower the signal slightly so we don't want to go into clipping. And there we have a frequency of 2.2 megahertz. So obviously we've got not enough turns on this coil. We need more turns. As you can see, as I vary the tuning capacitor, we vary the resonant frequency of the coil. So we've decided we haven't got enough turns on this coil. So what can we do about that? This is the thing. I've miscalculated this. Unfortunately, it's already got a core, a ferrite core, so we can't put a ferrite core to lower it. Now, what we can do, let's try increasing the amount of stray capacitance across the tuning capacitor. We'll increase the trimmer capacitance and we'll see what that does for us. Let's just try that again. So once again we'll go down to minimum capacitance and we'll vary the what's happening. Something's, oh, I see. Our coupling coil has come off. Let's try that. Let's try that. Right, there's the peak of our RF signal there. And we're now at 612 kilohertz. So this is immediately telling us that we need more turns on that coil, which is a bugger because I thought I had it pretty close. However, that coil has 160 turns, so I'm going to have to increase that, I think, probably to about 180. So I'll do that and I'll get back to you. But in the meantime, no, I won't get back to you. In the meantime, I'll talk a little bit more about this. The best, people worry about queue of coils. The queue actually doesn't affect the coil all that much. It's like using silver wire or special formers or anything like that. Actually has very, very little net result on that queue of a coil. The queue obviously is a quality factor of the coil, or just how narrow the resonance frequency is. Resonance is actually calculated on the 3 dB bandwidth. So for argument's sake, if that there resonating at 609, which it is, I'll get you up there. Now if we take that as 1, 2, 3, 4, there's about 5 divisions on the scope. If we go down to 2.5 divisions, that's called a 3 dB bandwidth. Now we've gone from 612 kilohertz down to 572. Now That's 5, 7, that's, what's that, about 40 kilohertz, say 50 kilohertz. I'm old, so my brain doesn't work that great these days, that's why I avoid maths, but if we say 50 kilohertz divided by 570 or say 600 kilohertz, which is the resonant frequency, if you divide 50s into 600, what are you getting? You're getting about 12. So 50 kilohertz goes into say 600 kilohertz 12 times. So that basically is the 3 dB bandwidth at that frequency. So if we multiply 12 by 600, we've got a Q there of 720. Would it be 720? I don't know, my maths is all up the boo-eye. But anyway, that's how Q is generally worked out. You divide the bandwidth by the frequency and you get the unloaded Q of the coil. This isn't actually an unloaded because we are pulling, by virtue of this coupling coil, we're actually pulling energy out of the coil. We're also damping the coil by this 120k resistor. So as I said before, it's extremely difficult to measure things without affecting what you're measuring. But you know, after a while you get a fair idea just how much a measurement will affect the circuit. It's a lot better now with, like, for argument's sake, high impedance voltmeters. In the olden days we had to account for a 2 or 3 k ohm per voltmeter. I think modern digital meters now, not that I like them very much, but at least they have a fairly high, I think they're about 10 mega ohm input impedance or resistance. I've got one of these, so I like these things. It's a volt ohm meter that uses a couple of ECC 81 triodes in there, and that's got an input impedance or resistance of I think it's 10 mega ohms as well. Analog meters are great. They're good for analog measurements, things like AGC circuits and varying voltage, because it's easier to watch a meter than a flashing digital display. You know, you can have an epileptic fit watching some of these displays, honestly. Okay, I'm going to redo this coil and I'll get back to you on that.